Hello everyone, let's discuss the concept of transformer under load condition. So last class we had a discussion that operation of transformer under no load condition. Now it's time for the discussion of transformer operation under load condition. So this is the circuit for the load condition. Before the discussion of that, first I would like to explain the summary regarding last lectures. Then only you are able to get clear cut idea about the concept. So we all know that first ideal transformer under no load. Okay, for that this is the core. So we have a supply voltage. This is open circuited because no load. So when we are going to discuss the concept of ideal transformer, what is the current through this? Obviously this is magnetizing component of current, mu or Im. Okay, mu or Im. Coming to this I2, which is equals to 0. Only the current present in the transformer is nothing but magnetizing component of current only. Mu or Im only. Okay, coming to practical transformer under no load condition. So coming to practical transformer, what we have? These are the windings and this is supply voltage like this. Let us take different sense. There is no load across secondary. Obviously, what is the current now? Now the current is what? I naught only, right? I naught, which is equals to what? IW plus I mu. IW plus I mu. Now it is IW plus I mu. Practical transformer under no load condition. So this is the summary for us. Now coming to transformer under load condition, what is the current? I1 should be equals to I0 plus I1 dash. So for ideal transformer, it is only magnetizing component of current. But coming to practical transformer under no load condition, we have what? I0. We have I0. But coming to transformer under load condition, we have what? I1. Now we have I1. V1 I1, which is the vector addition of I0 no load component of current and I1 dash. What is I1 dash? I will explain later. Self-induced EMF E1 and primary turns N1, secondary turns N2 and mutual induced EMF E2 and terminal voltage V2, because we have a load. We have a load. The load should be a pure resistive load or inductive load or capacitive load. So obviously there is a load, there is a current, some finite amount of I2 is there. So this flux is what? Due to alternating supply voltage or due to time varying nature of current. Okay, So first I would like to explain the theoretical concept. Later in detail I will explain the in-depth concept. So when the transformer is on the loaded condition, what will happen? The secondary of the transformer is connected to the load. So the load can be a resistive load, inductive load, or capacitive load, right? So the current I2 flows through the secondary winding of the transformer. The magnitude of the secondary current depends upon the terminal voltage and the load impedance. The amount of current through the secondary is totally depends upon the terminal voltage and the load impedance. By the variation of the load, we are going to get the different value of secondary current. So the phase angle between the secondary current and the voltage depends upon the nature of the load. See, the phase angle between V2 and I2, which is equals to phi 2. It's totally depends upon what? Nature of the load. That is the point. So by changing different types of load, we are going to get the different phase angle between secondary voltage and secondary current. So when the load is connected to the secondary of the transformer, obviously I2 flows through the secondary winding. The secondary current induces the magnetomotive force, that is N2I2, that is load component of secondary MMF. On the secondary winding, this force set up the flux, that is load component of secondary flux in the transformer core. This flux opposes the changes in main field flux according to Lenz law. Oppose the changes in main field flux. So this is the concept involved when we are going to connect the load across the secondary. So when the transformer under no load condition, the corresponding flux should oppose the changes in main field flux is nothing but what? The flux which is derived from the statically induced EMF. But when we are having a load, with respect to that load, there is a flux phi 2. That phi 2 should oppose the changes in main field flux. So when the load is connected to the secondary winding of a transformer, I2 is set up in the secondary winding. The magnitude and phase of I2 with respect to V2 depends upon the characteristics of the load. Only the load can decide the different phase angles of V2 and I2. The secondary current is in phase with V2 if load is non-inductive, that is resistive, right? Lags when it is lagging when the load is inductive, leads when the load is capacitive, that is pure resistive, pure inductive circuit and capacitive circuit. So this is ZL, this is variable load, like that. ZL variable load, right? This is ZL variable load, R and L, R and C. This is resistive load, not pure, just it is inductive load, right? Coming to this is capacitive load, not pure capacitive, simply it is capacitive load. So by variation of different types of load, we are going to get the different phase angle between V2 and I2. Obviously we are going to get different power factors. Just listen this statements. The secondary current sets up load component of secondary MM and hence it produces the magnetic flux phi 2, right, which is in opposition to the main field flux. We have already discussed this point. So the secondary ampere turns N2 I2 are known as demagnetizing ampere turns. So the opposing secondary flux weakens the primary flux. What is Lenz law? It should phi 2 should oppose the changes in main field flux. So the secondary opposing flux weakens the primary flux momentarily. This is called Lenz law. Hence what will happen? The primary winding back EMF even tends to be reduced. Why it is reduced? The opposition force is more than the required. Obviously the corresponding back EMF of the primary winding should be decreases. Obviously what will happen? V1 magnitude is more than E1. Obviously what is the condition? V1 should be equals to E1, that is minus is what oppose the supply voltage, but due to this Lenz law concept, V1 should be more than E1 and hence more current flow in the primary winding. See, V1 is more than E1, obviously there is a potential difference. Because of this potential difference there is a current. That current is called compensating current, which can be flow in the primary winding. So let the additional primary current be I1 dash. The other name of this current due to this V1 more than E1 is what? I1 dash, which is known as load component of primary current. Why it is named as load component of primary current? Why it is named as load component of primary current? Because of this phi 2 only we are going to get this. Because of this opposition force of phi 2, the net flux is reduced or back EMF E1 is reduced. So because of this, phi 2 is nothing but what? Load component of secondary flux. Because of this we have this condition, V1 is more than E1. So obviously the corresponding result is nothing but what? I1 dash. That current is called load component of primary current. So this current I1 dash is anti-phase with I2 because this is responsible for the production of this I1 dash. So it has to oppose this I2, not oppose the changes. It has to oppose I2 only. So this load component of primary current sets up its own flux phi 1 dash. Obviously when there is a current there is a flux, so which is in opposition to the secondary flux phi 2, but it is in the same direction as primary flux, and this flux, compensating flux, is equal to phi 2. Hence the two fluxes cancel each other out. I will explain in detail, don't worry, just go through these sentences clearly. So we can say that whatever the load conditions, the net flux passing through the core is approximately same as at no load. So due to the constancy of core flux at all loads, the core loss is also practically the same under all load conditions. Then phi 2 should be equals to phi 1 dash. Now I am going to explain in detail about this concept. Okay, or I can choose different. Listen carefully all of you. I would like to explain the clear-cut concept behind this terminologies. So what is the transformer under load condition? So this is the core of the transformer, right? For this core we have to provide the transformer windings. So let us choose, this is the winding. Okay, now here I am providing different sets of winding. Right, let us write, this is HV winding, this is LV winding. So for this winding I am providing a supply voltage. When there is a supply voltage, obviously that is the primary winding. When there is a load, obviously that is what? Variable load. So this is the circuit for the operation of transformer under load condition. So this is HV, when we have supply voltage, that is primary winding. This is LV, we have what? ZL. So for this V1, this is I1, which is equals to what? vector addition of no load current and I1 dash. So what is the current direction here? This is the current direction. So because of this primary supply voltage, there is a flux. There is a flux, right? There is a flux. Listen carefully. So what is this green color marker represents what? The flux phi. Okay. So here we are having a load. So obviously because of this load there is a current, right? Sorry, this is what? E1 N1 primary turns, like this N2 and mutual induced EMF, and this is what? V2. Clear? Okay, we have all parameters. When we are having a load, we are having V1 I1, V2 I2, E1 E2, N1 N2. So because of this supply voltage we are having, by using right hand thumb rule, we are having a flux. Clear? This is flux. Okay, then because of this I2, what is the sequence of operation? V1 I1. Now it is I1, not I mu, not I naught. Phi. Because of this phi, there is a E1, E2, then there is a load I2, I2, V2, right? So because of this I2, there is a phi 2. What is the current direction of I2? This is the current direction, right? So by using right hand thumb rule, what is the phi 2 direction? Which is opposite to phi, right? Which is opposite to this is phi 2. This is phi, this is phi 2. So obviously the resultant phi 2 should oppose the changes in phi. The resultant should oppose the changes in phi. That is, first I would like to draw. Sorry. So this is flux. What about phi 2? Phi 2 should oppose the changes in main field flux, obviously. This is phi 2, right? Phi 2 should oppose changes in main field flux, that is phi. That is the concept of Lenz law between phi 2 and phi. That is, the angle between phi and phi 2 should be equals to what? 90 degrees. Oppose the changes means what? 90 degrees. That's why we have this graph. So what is that meaning? Let's extend this graph. Now it is okay. It has to oppose the changes in main field flux. Now I would like to explain. This is what? Sorry. This is what? First quarter cycle, right? In this first quarter cycle, that is 0 degrees to 90 degrees. What is the strength of the flux? It is increases with respect to time, right? What is the statement here? What is the point here? The secondary, see, the secondary ampere turns are known as demagnetizing ampere turns. The opposing secondary flux weakens the primary flux momentarily. That is, in the first quarter cycle, what is the strength of the flux? It is increases with respect to time. So what is the function of phi 2? It has to oppose that strengthening effect. So it has to weaken that strengthening effect. Hence the primary winding back EMF E1 tends to be reduced. Now we have to explain this point. So in first quarter cycle, in first quarter cycle, what will happen? Flux is strengthening with respect to time, right? That is 0 degrees to 90 degrees. So what is the function of phi 2? Phi 2 should oppose the changes in phi. So what is the direction of flux? Let us take, this is the direction of phi. Then how can we get the direction of phi 2? It has to oppose the changes in main field flux. That's why the phi 2 should be acts in opposite direction, right? It has to, because phi is strengthening with respect to time. So in order to oppose this change, the phi 2 should be acts in opposite direction in order to satisfy Lenz law. So what will happen if phi is like this and phi 2 is like this? What is the statement then? See, the opposing force, the opposing secondary flux weakens the primary flux momentarily. Hence the primary winding back EMF E1 tends to be reduced. Why it is reduced? If phi 2 is more opposing in nature, ante kada, obviously the resultant flux, phi resultant should be, what is the phi resultant should be? Phi 2 minus phi, right? Because the phi 2 is more opposing in nature, so the resultant flux is there. So when there is a resultant flux, or we can say not like this, resultant flux, can we modify this statement? Not the resultant flux, if phi is more opposing in nature, obviously if phi 2 is more opposing in nature, can we write there is a reduction in back EMF, it's better. So obviously, therefore V1 should be more than E1, right? That is there is a potential difference between, that is there is a resultant voltage between V1 and E1. So that voltage is responsible to provide that is responsible to provide a compensating current, right? That current is called, load component of primary current, that is I1 dash. So because of this more opposing in nature of phi 2, we are going to get less value of induced EMF compared to supply voltage. So obviously V1 is more than E1, there is a difference in voltage. That voltage is responsible to provide a compensating current. So that current is called load component of primary current. So because of this, so V1 more than E1 due to what we are having, I1 dash. Because of this we are having phi 1 dash. So this phi 1 dash should oppose phi 2. Phi 1 dash should oppose phi 2 only. That is, phase angle between phi 1 dash and phi 2 should be equals to 180 degrees, not 90, because it is not opposing the changes in phi 2, only it has to oppose the phi 2. Because of that phi 2 only we are having the compensating current, right? The function of this phi 1 dash is to oppose phi 2 only. To nullify phi 2 only we are having phi 1 dash. Obviously we are going to get the constant value of flux. See, so because of this, for a moment V1 more than E1 and hence more current flow in the primary winding. So let the additional primary current be I1 dash, which is known as load component of primary current. So this current is anti-phase with I2, right? So in order to nullify this current, it has to act in anti-phase manner. So this load component of primary current sets up its own flux phi 1 dash, clear. So which is in phase oppositions to the secondary flux. So but which is in the same direction as primary flux. What is this? So what is the direction in first quarter cycle? So this is phi, right? What about phi 2? This is the direction of phi 2. Then what is the direction of phi 1? Phi 1 should be acts in opposite direction to this in first quarter cycle. Like this you can analyze in different quarter cycles. So the magnitude of phi 1 dash should be equals to phi 2. If phi 1 dash equals to phi 2, only phi is present in transformer core. So that's why we have this phi 1 dash. So what is the direction of phi 1 dash and phi? Same direction, right? What is the direction of phi 1 dash and phi? Same direction in first quadrant, not in all quadrants. The direction of phi and phi 1 dash is same in first quadrant only. That is the, see, but it is in the same direction as primary flux in first quadrant only. Okay, that's why if phi 1 dash which is equals to phi 2, only phi is present in the transformer core. So what about the operation in secondary winding, sorry, second quarter cycle? Listen carefully. In second quarter cycle, in second quarter cycle what will happen? The strength of flux decreases with respect to time, right? Let us take, this is phi. So what will happen? The phi 2 should always strengthen this flux phi 2, because the strength of flux is decreased with respect to time. So in order to strengthen this flux, it has to act in same direction of this flux, right? Then what about phi 1 dash? Now the phi 1 dash should be like this, it should be opposite to phi 2. Now the direction of phi and phi 1 dash is what? Opposite direction. So it depends upon the quarter, we are going to get the different directions of phi and phi 1 dash. In first quarter cycle, the direction of phi and phi 1 dash should be same, but in case of second quarter cycle, the direction of phi and phi 1 dash should be opposite. At any case, the function of phi 1 dash should oppose phi 2 only. In order to nullify, we have to provide the phi 1 dash. That is the case. So like that, you have to analyze the conditions for third and fourth quarter cycles. So what is the observation here? So this is flux phi. What is phi 2? It has to oppose the changes in main field flux, right? This is phi 2. Then what about phi 1 dash? It has to oppose phi 2. It has to oppose phi 2. That is, let us take it has to oppose phi 2. That is, the angle between phi and phi 2 should be equals to 90 degrees. The angle between phi 2 and phi 1 dash should be equals to 180 degrees. When it is 90 degrees, there is a concept of Lenz law. When it is 180 degrees, nullify the phi 2, or you can say phi 1 dash nullify the phi 2. So what is the condition? Phi 1 dash which is equals to phi 2, what will happen? So only, that is, main field flux is present in the transformer core, right? When phi 1 dash nullifies phi 2, therefore transformer is referred as constant flux device. Constant flux device. And what is this condition? Phi 1 dash should be equals to phi 2, which is equals to power balance condition. Power balance condition. This is the pure justification of transformer as constant flux device. Constant flux device. Okay, this is the best explanation of this concept. Now, okay, now I would like to explain summary. Listen carefully. What is I1? Primary. Just we have to remember this terminology, primary current. What is this N1 I1? Primary MMF. What is this phi 1, or you can say not phi 1, phi. Primary flux, that is main field flux. Clear? Next, what is I2? Load component of secondary current. What is N2I2? Load component of secondary current. Like this, what is phi 2? Load component of secondary, secondary flux, right? Clear. Next, what is I1 dash? This is very important. Load component of primary current. Load component of primary current. Like that, N1 I1 dash should be equals to what? Load component of primary MMF. Finally, phi 1 dash should be equals to what? Load component of primary flux. This terminology is very most important in order to avoid the confusion. Okay, load component of primary MMF. And one more important point. So this phi 2 should oppose this phi 1 dash. These magnitudes are equal. Next, what is power balance condition? Phi 1 dash should be equals to phi 2. This is what? Power balance condition. That is N1 I1 dash should be equals to N2 I2, right? N1 I1 dash should be equals to N2 I2. This is what? Load component of primary MMF should be equals to load component of secondary MMF. Clear? And last class I had a discussion that terminology of transformation ratio and turns ratio, right? Kindly do the modifications, or you can write here, kindly do the modifications in terminology of turns and transformation ratio with the following terminology, okay. Last class what I have explained, turns ratio, just you have to replace the turns ratio K with T, okay. T is equals to what? N1 by N2, which is equals to E1 by E2. Transformation ratio, which is nothing but K, which is equals to E2 by E1, which is equals to N2 by N1. That's it. But the relationship between turns and transformation ratio is what? Inversely proportional. Just you have to make the modifications when there is a T, just you have to replace the T with K. When there is a K, you have to replace that K with T. To avoid, for what? To avoid confusion in terminology in other textbooks. That's it. So to avoid confusion in terminology in other textbooks, that's only you have to modify the terminology. So when it is turns ratio, it is represented with T. When it is transformation ratio, it is K. So kindly do the modifications. In the earlier lectures. But this is the modification. This is the modification. Now from now onwards, transformation ratio is nothing but K, which is nothing but E2 by E1, N2 by N1. Coming to transfer ratio, N1 by N2, which is equals to E1 by E2. Okay, so don't write this lines in notebook. Okay, this is about the concept of transformer under load condition. So what is the important point here? I would like to give some brief explanation in briefly. If phi 2 is more, what will happen? The resultant flux is decreases. Obviously E1 should be decreases since V1 should be more than E1. So therefore I1 dash drawn, right, and set up phi 1 dash. Then some part of phi 2 is nullified. Some part of phi 2 is nullified. The remaining phi 2 opposes phi m, and above process continues until phi 2 is completely nullified by phi 1 dash. When phi 2, which is equals to phi 1 dash, supply will not produce further increase in current. So when phi 2 is equals to phi 1 dash, there is no current. So this is the brief summary of this explanation. So when there is a load, obviously there is a secondary current. Because of that current, there is a phi 2. That phi 2 should oppose the changes in this main field flux. So with respect to first quarter cycle, phi 2 should oppose this changes in main field flux. Obviously the dominant nature of phi 2 is more than phi. Obviously the resultant phi m is reduces. Therefore because of this V1 more than E1, there is a resultant current. That current is responsible to provide phi 1 dash. That phi 1 dash should oppose phi 2 only. So these are the different cases for first quarter cycle, second quarter cycle. Just you have to analyze with respect to third and fourth quarter cycles. And the phase angle between phi and phi 2 is 90 degrees. There is a Lenz law between phi and phi 2, but the phase angle between phi 2 and phi dash is 180. It has to oppose only. That's why phi 1 dash should be equals to phi 2. This is the power balance condition of a transformer under load condition. This is about the concept of transformer and under load condition. Thank you.